the Badlands of northwestern Montana. Dinosaurs, they lived once, a long, long time ago. They were masters of the earth. There were no cameras to photograph them or people to watch them. There were no hunters to hunt them until now. Scientists are the dinosaur hunters. They walk and sometimes crawl the landscape looking for clues to the mysterious past. They hunt with pick and shovel, and especially their imagination. Jack Horner from the Museum of the Rockies in Bozeman, Montana, is a paleontologist, a scientist who studies ancient plants and animals.
I think the reason anyone gets into dinosaurs is because they're mysterious. I think that the dinosaurs are probably the one animal that's left on Earth, as so to speak, that we really do not understand as an animal. And so, if you are biological, if you are the kind of person that likes biology and geology, and you're also the kind of person that likes a good detective story, dinosaurs are the way to go. And I think that's the thing I liked when I was young. And that was one thing that drew me into wanting to study dinosaurs, was just the real mystery of it all.
The Badlands is a rugged and forbidding landscape that holds the key to understanding the lost world of dinosaurs. A grand adventure awaits the dinosaur hunters, and though the work is hard and long, it is a labor of love.
It's one thing about paleontology you have to remember. Working hard is fun.
Just keep thinking that.
That's right. We claim we work hard and we play hard and we have fun doing both.
Camp Makala is located in the Badlands of northwestern Montana in the vicinity of the famous Egg Mountain site. In the summer, the Museum of the Rockies conducts a paleontology school where students learn to hunt and dig dinosaurs.
Welcome to the Camposaur pit, and today we're going to be digging dinosaurs. We're going to be after the Maiasaur dinosaur. We theorize that there's a herd of about 10,000 of these Maiasaur dinosaurs running around in this coastal plain area. As they were running around, the volcano out there towards the west, about 10 times the size of Mount St. Helens, erupted. As it erupted, it had a huge ash cloud, and this ash cloud then consumed the dinosaurs. But something happened next, all right? And we're not sure what happened, but this is the theory. We find the bones disarticulated down in the bone bed over here, all right? In other words, the bones are not together anymore, okay? So therefore, we theorize that these bones have been transported. Okay? Otherwise, you'd find the whole dinosaur, right? So a study has been done on the orientation of these bones. And the bones are oriented to the fact that we think that the stream moved from the west to the east. We know this because all the bones seem to be lying in an east or a north-south direction because they rolled with the current. They're not going to go end over end with the current. They're going to roll. So again, this is how we know that the bones have been transported. Something else about these bones are busted up a little bit. And again, this is probably due to the movement of the water breaking up these bones against the rocks as the bones clashed into each other. We refer to this area as a sort of a dinosaur junkyard because we find all kinds of different dinosaur parts. You know, in fact, today when you guys are digging, I guarantee you you're going to go after one bone and you're going to find 2 or 3 others just trying to get that one bone out. Okay, which is pretty exciting. All right, this is an excellent pit for you guys to be digging in. So these bones were all deposited in this, we probably figure this is a sort of a valley area. This was some 80 million years ago. Bones were deposited, all right? Then we had some more tectonic forces at work here. Okay, well, this is part of the Willow Creek anticline, and these sediments are about 40 feet deep. What happened, the tectonic activity in this area has deformed the land, and it deformed it into an anticline. In other words, the land buckles up like this. As the land buckled up, we had, for the past 4 million years, we've had glaciation. This glaciation has eroded the top of this anticline away, and also this anticline has sort of fallen off to the side, thus exposing all these sediments then that were once underneath the ground. Really, without the Willow Creek anticline, we would not see these bones. We couldn't afford to dig down this deep to find them, for one. So we really depend on geological processes that occur naturally to expose these bones. The instruments we're going to use today, of course, are as simple as an ice pick. And what I want you to do is sort of pretend you're a dentist, and you're just sort of, as the dentist picks away at your teeth, but you're going to pick away at the bones, all right? So, first thing to do is get a kneeling pad, probably, because this stuff is pretty rough on your knees. And what you want to do is go ahead and work next to the bone. We want to do to the bone is to what we call pedestal it, sort of make a mushroom out of it, all right? We want to leave a nice section, maybe about a ½ inch to an inch on each side of the bone, okay? Then we're going to go dig down on the side of the bone. Just take your time like I'm doing right here. Then once you get some rock debris or some of this bentonite removed, all this stuff is all volcanic ash, just take your broom and just brush it away. Then when you get enough, go ahead and brush it into your dustpan and into your bucket because we want to keep our site real clean. And when your bucket gets full, there's a wheelbarrow right behind you there. Just go ahead and fill up the wheelbarrow and I'll take care of that. I'm going to go ahead and dump it in our parking lot later on today. If a bone gets really brittle on you, what we have here is what we call butt var. It's a resin with nylon in it. And what you do is go ahead and just pour it on the bone. This acts like a hardener. Okay, keeps the bone together from cracking into little pieces. After these femurs are all taken down, the next step is to go ahead and plaster them. Okay, what we do there is we take some burlap with plaster, all right? Take the burlap on top and we plaster over it to make a jacket out of it. And this is so we can go ahead and remove the bone from the ground.
Summer is short in the northern Rockies. When the field season is finished, all the specimens are brought back to the museum where researchers spend long winter days cleaning the bones and piecing together the scientific puzzle.
A good part of our information comes from uncovering these bones and what you see right in the ground. You know, what is happening here? Is it a bone assemblage? Is it just one dinosaur? You know, whatever. And you want to collect a lot of samples, get an idea of the environment that it died in or what they died in and so on. You bring all that information back, and then the staff, with students and volunteers and so on, sits down and prepares the bones. And that is really, really time-consuming. A lot of people get the idea that we bring these bones in and just throw them up on exhibit. To give you a good example of how difficult it is, we've been very successful in collecting, but we've only really prepared about 40% of our collection. And what it is a three-dimensional jigsaw puzzle that is in many, many pieces. Out in the field, we usually are collecting dinosaur bones in various sedimentary rocks. It's usually a sandstone or a mudstone. And as you had seen, especially from Egg Mountain in that area, we were making plaster jackets. That was to stabilize the bone. Now, when those plaster jackets come back to the lab, they're opened up from the bottom, and here you can see we have a mudstone. And a lot of the bones are usually very fractured, but the preparator face is basically a three-dimensional jigsaw puzzle. And you can see here, there's lots of bits of bone that had to be cleaned up individually and then reattached. So it's a very long and tedious process. We use different consolidants. Most commonly is a liquid plastic called Vinac to stabilize and harden the bone, but then we use adhesives like epoxies and so on to actually attach all of these fractured segments. So this is one process that the preparator is faced with in the laboratory.
What we have here are a range of sizes of the humerus, which is the upper arm bone of Maiasaur. 3 of these bones were recovered from the bone bed at Egg Mountain, which is estimated to contain approximately 10,000 individuals. The smallest bone was recovered from one of the nests, the Maiasaur nests that we find pretty close to the bone bed. As you can see, they're all pretty badly broken. This is a consequence of the way that they were transported to the area. You can see here, part of this one is missing. If you compare it, you can see that this end, which is the elbow end, if you like, the distal end of the humerus, is completely missing. So if this bone was complete, it would perhaps be this long. You can compare with the smallest one that we have. All the bones are broken because of the way they were transported to the area in the morass of volcanic mud and water that swept them in. As a consequence, they were bashed against each other, bashed against rocks in the mud flow, and they were pretty badly broken up. And the preparators here in the museum have painstakingly glued them back together so we can get some idea of their original shape.
We're in the histology lab. Here, the specimens are taken. They're embedded in a plastic, and then they're placed on a machine such that we can cut very thin wafers of bone. These wafers of bone are usually about 1 millimeter in thickness, and then they are further ground until they are very, very thin. These specimens can then be placed on the microscope, and we can see the microscopic detail of the bone. What we have on the screen is an image of dinosaur bone as seen on the microscope. The image that we can see through the oculars here is picked up by a video camera and then taken to a computer. This image is then processed into a digital image and projected on the screen. The nice thing about this system is that we can then take this image, call up certain programs, and actually measure points on the histologic slide. We have here a large packet of bone. We can measure
from one point to a second point, and then on the screen see what the diameter of that packet of bone is. Of specific interest to us is not so much the size of the bones, but the holes where the vessels lay. Here's a very large canal. We can measure that and get an idea as to the size and shape of these vascular canals. A very good example of how we use this machine and the system of looking at the quality of bone is with the duck-billed dinosaur Maiasaur. What you see on the screen right now is a microscopic picture of the bone of a nestling. This is an animal that was in the nest. And you can see there's a large amount of holes in the bone indicative of fairly rapid growth. We can compare this to an older dinosaur and see how the bone has changed. Now, it is not as porous. There is more bone. And when you get up to the adult, as we had on the first screen, you can see the type of bone that's being formed. We get an appreciation of how rapidly the bone is growing, what it looks like as it is growing, therefore giving us some idea as to the rate in which the animal is growing, and find out at what stage they reach certain easily recognized characters in life. For example, juvenile, subadult, or the adult full-grown animal. This gives us an idea as to the type of bone that a specific dinosaur had, how rapidly it was laid down, and the changes that occurred as the animal grew up. We can then compare this with animals that exist today. It is this comparison between animals of similar growth stages that allows us to draw conclusions about growth. So in this instance, we can see on the left, we have a very young, large-growing bird, the emu, at 1 month of age. We have an alligator on the right, somewhat older, about a year to 2 years of age. And in the middle, the Maiasaur nestling, a very young dinosaur. So we can compare dinosaur against reptile, dinosaur against bird. We can also do this when they get older. And at a higher magnification, look at a juvenile Maiasaur, still rapidly growing, and here, with a reptile, an alligator that is known to be 2 years of age. Very different type of bone. And it is this comparison between animals of similar growth stages that's important for drawing conclusions about the physiology of dinosaurs.
The pieces of the dinosaur puzzle take shape both scientifically and artistically. Montana artist Doug Henderson has worked closely with Jack Horner and the museum staff, resurrecting the world of dinosaurs before our very eyes. 65 million years ago, dinosaurs as we know them ceased to exist. One popular theory suggests that a giant meteor collided with the Earth, causing a tremendous explosion which sent dense clouds of dust and volcanic ash into the atmosphere, cutting off the life-giving rays of the sun. Horner makes a convincing argument against meteorite impact as the cause of dinosaur extinction.
Extinction of dinosaurs. Now, a lot of people subscribe to the new old theory that you have to have extraterrestrials wipe out the dinosaurs. That's right. So you bring in a 6-mile, 2-mile, 4-mile wide asteroid, crash it into the Earth, you blow a bunch of dinosaurs and trees and crap like that up into the atmosphere and block off the sun, and then the plants die and the dinosaurs die, and it all looks like it works real neat. But unfortunately, when you go up through the geologic record, we do have a neat little layer, the iridium layer, they call it. And the iridium layer apparently was laid down when this meteorite hit the ground. We have never found a dinosaur skeleton at that boundary. There's never been one found on Earth anywhere at that time. In fact, there has never been one found within 3 meters of that boundary. So if we just use positive evidence, which scientists are supposed to only use, we're not supposed to derive our theories on negative evidence. If we just use positive evidence, then based on the information we have right now, the dinosaurs went extinct before something collided with Earth. So there's no way to say that an asteroid caused the extinction.
What other kinds of natural phenomena could have caused the dinosaurs to become extinct? How do we know what they looked like? What they ate? How they lived and died?
Always wanted to know about their behavior. And I'm sure there are a lot of questions left in their behavior that we haven't answered yet. I think the biggest question I have has to do with their evolution and what causes particular animals to evolve while others don't. Or all animals evolve, but what is it that causes what we call punctuated evolution, when we have a fast spurt of evolution, while other animals just are evolving real slow?
There is a word that every scientist knows. The word is serendipity. It means an aptitude for making desirable discoveries by accident. But it is never wholly by accident. A scientist must put him or herself in the position to experience serendipity.
I walk around in the field asking myself questions all the time. And some of them are probably, but some people might think is pretty stupid questions. But in this field, nothing is a stupid question. Especially something that people think already is answered.
They must be curious almost to a fault. They must try to be open-minded and free of bias. And most of all, they must be patient.
20 years ago, no one would have ever thought of asking, are dinosaurs really cold-blooded? Everyone would have thought that was a really stupid question. Because of course they were, right? Yes. That's right. All dinosaurs drug their tails.
Paleontologists and other scientists at the Museum of the Rockies are immersed in dinosaur studies, and serendipity lurks within the geology and fossils of each new find. If you are not involved in the quest for knowledge and understanding, you may never experience serendipity. But it is there, waiting for you to accept the challenge, just as fossilized bones waited to tell scientists the story of the lost world of dinosaurs.